Hi everyone, welcome to my YouTube channel Everyday Space. I am Dr. D Mohanty and today we'll discuss about the vapor compression refrigeration cycle with wet vapor after compression. In the previous lecture, we have discussed in detail the vapor compression refrigeration cycle with dry saturated vapor after compression. So in this lecture, first I will show the cycle with the help of temperature entropy and pressure enthalpy diagram. So first I will draw the TS diagram or temperature entropy diagram. This is actually your saturated liquid line and this is your saturated vapor line. So before this line it is all liquid and after this line it is all vapor, and in between it is a combination of liquid and vapor. So now I will draw the TS diagram. So we do have four processes. This actually represents your pressure enthalpy diagram. This actually represents the saturated liquid line and this represents the saturated vapor line. This is the compression process. This is the condensation process. This is the throttling process. And this one is your evaporation or refrigeration process. So 1, 2 actually represents the compression process. And both the TS diagram and PS diagram actually refer to the thermodynamic processes undergone by the refrigerant, which is actually the working substance in any refrigerator. First, the refrigerant will enter the compressor. In the compressor, it will be compressed, and due to compression, its pressure and temperature is raised. That you can observe from both TS diagram as well as the PS diagram. T2 is more than T1 and P2 is more than P1. Due to compression, its pressure and temperature is raised, and then it is taken to the condenser where the condensation takes place. Here the refrigerant actually delivers heat to the surrounding condensing medium or cooling medium, and this takes place at constant pressure. Particularly for this cycle, it is a constant pressure as well as a constant temperature process. After that, the refrigerant is taken to the refrigerant control valve or throttle valve where it undergoes unrestrained expansion or throttling. In throttling, the temperature and pressure both drop, but no work output is obtained. And after that, it is taken to the refrigerator or evaporator, and as its temperature and pressure is significantly reduced, it receives the latent heat from the space to be cooled, and as a result its condition changes from 4 to 1. In this particular case, the dryness fraction is actually increased significantly, but it never attains a complete saturated vapor condition. And as far as the coefficient of performance is concerned, all of us know that the coefficient of performance or COP is the ratio between the refrigerating effect divided by the work done. And we will actually represent the refrigerating effect in terms of enthalpy differences. The refrigerant actually enters at 4 and it leaves at 1 as far as the evaporator is concerned. So the enthalpy difference is H1 minus H4 as far as the refrigerating effect is concerned. And as far as the work done is concerned, it is the work that is done in the compression, because we do not get any work output when it passes through the refrigerant control valve or throttling valve, because this is an isoenthalpy process. So compression work is H2 minus H1. Now, as it is an isoenthalpy process, the throttling is an isoenthalpy process, your H3 and H4 are same. So you can represent this as H1 minus H3 divided by H2 minus H1. Now, this 3 is lying on the saturated liquid line. So you can substitute H3 by HF3 divided by H2 minus H1. Now, you can easily compute H1 as well as H2. H1 is equal to HF1, that is the liquid heat, plus dryness fraction times the latent heat. And you should remember that here T1 is equal to T4 and here T2 is equal to T3. Similarly, H2 is equal to HF2 plus X2 into HFG2. You can substitute these values and find out the coefficient of performance of the cycle. And if you know the dryness fraction of either 0.1 or 0.2, the other value can easily be computed, because PS1 is equal to S2, because 1, 2 is an isentropic process. And as far as S1 is concerned, S1 is SF1 plus dryness fraction times HFG1 by T1, and S2 is equal to SF2 plus X2 into HFG2 divided by T2. So even if you know dryness fraction of 1, you can find out 2, and if you know the dryness fraction of 2, you can find out 1, because you can compare both the equations as H1 is equal to S2. So this is all about the vapor compression cycle with wet vapor after compression. If you compare this with the previous lecture, the only difference is that it is not attaining the saturated vapor state after compression. Otherwise, all the other processes are exactly the same. Thank you very much for watching this video. If you have any doubt related to this, please do put questions so that I will try to answer. Thank you very much for your support. I would request you to subscribe to my channel if you have not done so till now. I would further request you to share this video with your friends and relatives. Hope to see you soon for another lecture on my YouTube channel Aerodecimus.